We learned something about line integrals. We know a bit more how to calculate surface integrals, and now we put everything together. We will learn about three important theorems of the vector calculus. They are really the cornerstone of the subject because they really bring together line integrals, surface integrals, volume integrals, and the differential operators we learned. So this really brings things together, so that's exciting time. And we start with the theorem number 1, which is the Gauss or divergence theorem. What it does, it connects the volume integrals and the surface integrals. Let's take a vector field f and some volume with a closed surface, such as a ball, right, or which has a spherical surface. The theorem states the following: if you take a surface integral over the surface of that volume, it's the same as to take the divergence of this field and then integrate it with respect to a volume. So take the volume integral of the divergence. That's curious, and that's not entirely obvious. I have to say we do not prove these theorems here, and you don't have to prove it. But if you're interested, you can look at the materials such as Helm, where is some indication of the proof available. But we still can interpret what does it mean? What are the physical and engineering meaning of this? Well, the surface integral is a double integral, and the volume integral is a triple integral. And we can use the fact which we used previously for the surface integral. We can take a little element of the surface with the right orientation, taken by the two principal tangent vectors. And then we can write equivalently the divergence theorem, saying that we have a surface integral of that that scalar product of f and n, and the triple integral of the divergence. And you can remember perhaps that divergence is some measure of expansion or contraction, and the theorem therefore represents a conservation law. So if you have some material which disappeared from this volume, it must have gone through the surface, and we can measure the flux across that surface. So the surface integral measures the flux which went outside or went inside this volume, and the divergence measures how much stuff appeared or disappeared. So you can picture it as you have your sphere, and the amount of stuff left this sphere was the flux, and this flux is, as a vector, is given by this integral over the surface. And the divergence shows you the rate of change of that. So you can think of, for example, a gas expanding and leaving the volume. Now the second theorem is called the Stokes or Kevin-Stokes theorem, and that connects the surface integral and the line integral. Let's say that we have now a surface with some boundary. It's not a closed surface, it's just a surface, can be curved of course, and it has some naturally closed boundary which we call contour C. And what the Stokes theorem states is that if you take a curl of that vector field and integrate it over the surface, it's the same as to calculate a line integral of that vector field along the boundary. Again, it's a very powerful result. It's not obvious at all. It connects the surface integration with the line integration, and it also involves the curl. And this surface integral is a double integral, and the line integral is just standard definite integral. And we can think that the curl is some measure of rotation, amount of vortices, and we integrate over the surface to get a feeling of what is the total amount of rotation, while the line integral estimates the so-called circulation of this vector field. And this states that the amount of total rotation integrate over the surface is the same as circulation of this vector field over the boundary. And that's very useful, for example, for conservative fields, as you have seen that for them the circulation of vector field will be 0. But important again here to bear in mind that then you compute the integrals according to the Stokes theorem. You take a closed contour, but not necessarily a closed surface. So the surface actually has to have a boundary for you to apply this theorem. That's important to bear in mind. And this brings us to the last theorem, which is the Green's theorem. It's defined in 2 dimensions, unlike the previous 2 theorems, which are 3-dimensional. And let's say we are looking for that position vector. And let's take a curve, a closed curve, in a plane, in an xy plane, like that. So let's take a curve with an area A. And what then we have is that for a vector field, again in 2D, we don't have third component, so just first component, second component, we connect again a line integral and the surface integral, but with a slightly different looking expression. So for a given vector field and for a given curve that bounds the surface in 2D, just a plane surface, we can state this fact. Well, this actually we can comment about. That's just a direct result of the Stokes theorem. In fact, if we take our surface element so that it lies in a flat plane parallel to xy, say at z equals 0. So if you take your plane of integration like that, so z is constant, and then every element will have a normal pointing towards z direction, and then the only remaining interesting bit of that surface will be the z component of the curl, which will give you the right-hand side expression for the Green's theorem. And on the left-hand side, we take the little element of the boundary as we move along, right, as we go over in the xy plane. So if we take a little element dr pointing, say, this direction, then it will only have 2 components, and that brings us to the left-hand side of the Green's theorem, and therefore we show that it's just direct result of a Stokes theorem in 2D.